Well, folks, let me introduce myself. My name is Neeraj Kaul. I am a VP of Engineering in the SRG, that's Silicon Realization Group at Synopsis. Well, today, let's look back a little bit on the Moore's Law. So most of you are familiar with the Moore's Law and the advances it has done in the last few decades, advancing our innovations and bringing more technology into the system. Now, in the next few, maybe we'll say about 40 minutes or so, I will be walking you through something which we call SysMoore era, an era of new complexities, an era of new advances, an era of new opportunities, and what we are at Synopsis doing to tackle some of these challenges, and what are the new technologies that are coming up. So let me walk you through the entire system. So let's get started. So before we go into the SysMoore era, let's look at the landscape overall. The landscape of multiple verticals that are happening all around us. Networking, data centers, mobile, power, AR, VR, all these verticals that are happening around us, there's a tremendous amount of digitization or digital transformation, if you will, that has been happening in the last few years. And this transformation has happened at a scale which is unprecedented. It's actually a lot faster than what we have seen in the past in the few decades. So it's really, really gone so fast. I mean, if you can imagine on the healthcare system, the advent of COVID-19 vaccine, how fast it was developed. In fact, the Omicron vaccine will be available in about 2 months. So the speed of development, the compute power that is available now for these innovations is tremendous. The amount of data that is being either sensed, or it's being processed, or it's being transferred around these systems in this scale of maybe, let's say, petabytes or zettabytes, that amount of data is requiring us to examine and re-examine our way of computing. So we really need new ways of computing, really need new ways of dealing with the situation. Now, with all those demands that have happened in the last several years, I mean, we are at the chip shortage era right now, but there's so much demand. What is happening is the number of design starts have started to accelerate at a rapid rate. And when I say number of design starts, it's not only the semiconductors that already have existed for years and years, but also new design starts, new entries into the entire system. So that's putting a lot of pressure on semiconductor industry, and obviously that requires some new thinking, new ways of dealing with the situation, and providing new solutions for our customers. So let's look at this in a little bit more detail. So while these are verticals, there are certain things that all of them do horizontally, common. First thing is the push for PPA. So the power, performance, and area. I think most of you have dealt with it. You're squeezing power, performance, and area almost every day on your chips. Now we're going to add a couple of more letters to it, C and T, which is the cost and turnaround time or time to results. So PPA, CT is becoming a challenge for all of these verticals, and they're dealing with them almost every day. The second is the custom silicon. Now, in the past, when you embark on a new application, you use a generic microprocessor or generic chip to deal with the situation and run your software on it. But with the advent of, with the requirements of PPA, it is becoming imperative that custom silicon and custom design, custom architectures are built for each of these verticals. So gone are the days we can use a regular microprocessor. You really have to design it for that particular vertical, for that particular system. Other aspect of these verticals is vertical integration, which means looking at the entire system from software all the way to silicon, the whole process, and optimizing each one of these elements at each stage, optimizing the interfaces between them, and considering the entire end-to-end vertical solution. So PPA, custom silicon, vertical integration, and then there are some specific challenges that have come up in most of these verticals. As these challenges, I think some of them were talked about in the panel earlier, the security. I think these verticals, many of these, like data centers, like automotives, they require safety and security. They require power, performance per watt. They require resilience. Resilience essentially is mean time to failure, the longevity of the chip. These are some important metrics, important considerations that are happening beyond PPA for most of these verticals and applications that we see today. Now let's look at the Moore era and what has changed in the last few years. So over the last several decades, Moore's law has been performing very well. I mean, we've seen year after year, every couple of years, you see 2x improvements in PPA, and it has actually consistently delivered on what was expected. So that's great. I mean, enormous innovations in this era, and we've all lived through it for many, many years. So what are we seeing now? In the past couple of 2 to 3 years, we're seeing a slowdown, a flattening of the curve in the Moore curve. So as the nodes become smaller and smaller, 5 nanometer, 7 nanometer, 5 nanometer, 3 nanometer, and below, PPA is getting very difficult to achieve just simply by moving from node to node. Two particular metrics, power and performance, are not necessarily scaling at the same rate as the previous Moore's law was. So we are only seeing about 15 to 30% improvement as we move from node to node. In the past, it was almost 2x. So power and performance are becoming a bottleneck as we move from node to node. At the same time, the scaling, which is the area of the chip, is scaling, continues to scale at 2x. So there is definite benefits in moving from node to node. However, there is challenges in meeting the power and performance metrics just by moving from node to node. But the hunger for power and performance has not stopped. I mean, with the advances in verticals, with the demands we have in semiconductors, with the amount of data that is being processed, new chips in AI and automotive being designed, the hunger for power performance remains. So obviously there's new ways we need to think about in terms of reaching the goals that our customers and our industry needs. So that's where we come to the era of SysMoore, an era of systemic complexity, an era where we need to find new ways of dealing with the situation and unflattening or maybe unbending the curve, if you will, so that we continue to advance in the same way that we've been advancing in the past. Of course, it takes a lot more techniques beyond just node-to-node migration. It takes innovations in multiple different areas. And the three that I have shown here are key. One, I think I mentioned earlier, domain-specific architectures. You cannot just use generic systems. You have to squeeze performance and power from individual applications. Look at the applications and tailor your designs and architectures for that system. So that's becoming extremely important. The second aspect, concept is 3D IC design. Well, I think the bottlenecks in terms of communication with external devices is becoming high, and there's a need for bringing all the chips together, integrating them in such a way that the communication becomes much more fast, die-to-die communication, die-to-memory communication, that actually becomes a lot more efficient by aggregating these chips, integrating these chips in an efficient way. Of course, this entails not just integrating them, but the whole system analysis and other effects that come into play. But 3D IC concept is playing a major role in terms of pushing the curve up. And last but not the least is AI. So in the past, the EDA algorithms have used standard algorithms to tackle some of the NP-hard problems that are prevalent in the EDA industry. Well, of course, you use heuristics, you use lots of approximation algorithms, but with the advent of AI, there's an immense opportunity to augment these algorithms so we can get better results, better PPA, more optimal results, much faster results. And the use of AI, use of 3D-IC, use of custom domain-specific architectures are key to pushing the curve up in this SysMoore era. Now this is coupled with getting PPA is one part of the story, but there's a twin part of the story, which is engineering cost. Moving from node to node, 3 nanometer, 2 nanometer, is becoming a lot more costlier in terms of the engineering costs. The number of engineers you need to use to design your chips is increasing at a rapid rate. The number of amount of compute you need, the time it takes. So the overall engineering cost is pretty high. Now, you don't have unlimited number of engineers available to you. So you just can't scale. There's no way. So it's a showstopper. So essentially, there's the techniques that we are using to improve PPA. We also need techniques to improve overall productivity of the system so that you really don't need 2x or 3x number of engineers to combat these problems. So the twin effect of PPA as well as engineering cost. Now at Synopsis, we have looked at this era and what we need to do in a number of ways. And we've come up with 6 vectors. 6 vectors that will power the era of SysMoore. These vectors are essential to push the curve up. There's an X sign in the middle, which essentially tells us these vectors will be multiplied together to give you the boost that you need. So overall boost that is needed to get the PPA and productivity is using the product of all of these vectors. And these vectors, what are they? I've highlighted some of them already. One is the domain-specific architectures, so you can't get away from it. I mean, you've seen some of the TPUs are about 10x better performance than standard GPUs that were used in the past. So obviously, using specific design architectures are very important to get to the SysMoore era. The second is energy efficient design. Now, devices are power hungry, and power has become the first order metric in our computation. So when we are closing designs, doing timing closure, you cannot ignore power. Power has to be computed from the very beginning and incorporated into your cost. Now, the Moore's law, as you go from node to node, there is some power benefits. It's not zero, but there is some power benefits. But more needs to be done. One is from software optimization. The other is from the EDA algorithms themselves. So these combined will need to be used for energy efficient designs. Third vector is the Moore's law itself. Of course, it's not stopping. It has slowed down, yes. The curve has flattened a bit, yes, but it hasn't stopped. So we are still continuing to move from node to node and introducing new effects that need to be tackled during your design solution. Now, new device parameters, new device effects, GA, gate all around. You have mixed rows and multiple different things that come up that need to be factored in, that need to be coded in your EDA algorithms to be able to handle some of these advanced nodes. So Moore's law continues at a slower pace. However, we need to work with the foundry system to enable them more effectively. Multi-die 3D-IC, as I mentioned, is another major vector. Designing and integrating chips, chiplets, and disaggregating chips and chiplets, focusing on die-to-die latency, focusing on die-to-IO memory latency is important, looking at the overall system, power consumption, and things like that. Another vector is silicon life cycle. What is this? In the past, much of the work was done after you tape the chip out. You're done, chip has gone to the field, you don't worry. But then, in order to take more advantages of your chips and improve their performance, and also look at the failures of the chips, silicon lifecycle management becomes absolutely crucial in this era. Essentially, as the chip goes into the field, you constantly have to monitor what they're doing, get the data out of those chips, and then use that information to further improve your PPA of those chips. Not just PPA, but also the resilience and longevity. And the last but not the least vector is cloud and AI. With the advent of cloud, you have immense compute power available to you. So much of the algorithms that we have used in the past are being tailored for cloud, so you can take advantage of this compute infrastructure you have, take advantage of elasticity, take advantage of spot availability of new compute machines. These things are important to also factor in to get to the SysMoore era. And of course, AI, as I mentioned, AI methods, big data, data processing, all of these combined together, if you factor all of them in, are essential for us to move to the SysMoore era. Let's look at it at these 6 vectors in a more detail and see what Synopsis is doing to offer solutions in these vectors. The first one is domain-specific architectures. The architectures that are tailored towards specific design styles, specific verticals. For instance, AI vertical, so graph core, intelligent processor unit. The ability to design or take an architecture that can deal with large amounts of data efficiently. I mean, if you use a general purpose processor, a lot of the computations you do are probably unnecessary. You're just wasting power. But if you actually designed it for the specific purpose, then you can actually reduce the power. You can have a better TAT. You can get better performance. So all of these customers that are designing domain-specific architectures, especially in verticals like automotive or AI or mobile, they are taking the approach of domain-specific architectures. So what are we doing to enable them? So we have a number of technologies and number of products that are available to some of these customers to take advantage and decide the right architecture for that particular vertical. Platform Architect is an architectural level exploration system. So in the beginning, when you don't have a lot of information, you're still trying to explore what's the best way to architect my design. What are the different configurations I may have? Platform Architect allows you to do that at system level. This is followed by RTL Architect, which is another level of exploration at the RTL level when you're designing the right RTL structure. What are the constructs you should use? What is the best possible way to design RTL so you get the best possible PPA at the end? Floor plan exploration. All of these exploratory techniques early in the flow are absolutely crucial to define your right architecture for your specific domain. Here's an example of one of the customers, computing customer, that was able to use our RTL Architect product and technology to reduce the iterations, actually explore a lot bigger space up front to choose the right RTL architecture to go forward. In fact, they were able to get 5x faster TAT than what they had done in the past. And in the end, they were able to get 300 megahertz more frequency. So this is the kind of work you have to do. Besides, implementation and squeezing power and performance at every gate, at the architecture level, at the RTL level, exploration is key. So one of the things you also need to consider here is while you're exploring, the decisions you make need to make sense. They need to follow through as you go through the entire flow. So whatever results you're getting out of Platform Architect and RTL Architect are fully correlated with the entire system. So in this particular design, the correlation was over 90%, which means the decisions they made in the early parts of this flow they were able to hold through the downstream flow. Extremely important for exploring your architectures in the early part of the flow. The second part of the challenge is the scaling challenge. The scaling itself is the continuation of Moore's law. Again, as I mentioned, as you go from node to node, 5 nanometer to 3 to 2, there is a challenge. There's new effects that come in. There are new rules you need to deal with. So there is a scaling challenge that we need to continue to scale. So in the past, we have had a traditional method of implementation. Synthesis first, and there's a handoff from synthesis to place and route. There's a handoff from place and route to sign off. And there's clear boundaries as to what is done at what point in time. Now, this worked when the nodes were larger. There was a situation that people would use to hand off, and it was okay. But now, with the advent of smaller geometry technologies with variations and other effects, physical effects, small geometry effects, these are causing for us to look at this, what was called the second order effects in the early parts of the flow. For instance, placement rules, from 1D placement rules to 2D placement rules, to diagonal placement rules, to context-based timing, context-based power, all those things are so crucial to consider up in the early stages during synthesis. You just cannot wait till the end. But how can we do that? All the tools that in the past have been separate. They've been, their models are different, their database is different. So that actually poses a challenge. In Synopsis, what we are able to do is to tackle that problem. So essentially the problem we have in the traditional ways is it requires a lot of iterations, it requires a lot of margin generation, and then a lot of time lost, and you leave PPA on the table. At Synopsis, we have created what we call a hyper-converged system from RTL to tape out. We term this as the Fusion technology and the Fusion platform. Essentially, synthesis, place and route, sign off are all part of a single system in the Fusion compiler flow. They're built on the same data model, they work on the same model, they see the same cost, they see the same effects. So you can actually be certain that what you're doing at synthesis is exactly what you will see at the end. And all of that is powered by the golden sign-off, which is Primetime, Star, and the tools you use today. Now there's also an opportunity not only to see the effects, but also an opportunity to move technologies around with this single data model system, which means synthesis can be applied towards the later stages of the flow. You can bring in detailed routing up into the flow. In fact, many of the customers do that. They detail route some of the signals early, even before synthesis, to be able to take into account those effects much earlier. So this single system that enables you to look at the entire situation at the same time in the golden sign-off flow is the benefit you get with the Fusion technology. This is augmented with what we call the AI-driven PPA, design space optimization. So besides running tools, besides really generating PPA by squeezing algorithms, there's a number of things that our customers and users do. They explore hierarchies. They explore settings in the tools. They explore flow variations. They explore many different things, floor plan variations, to see what is the best possible PPA you can get out of the same tool. But that takes time. And in fact, they cannot explore the entire space. So what can we do? We can help them with the AI system, the design space optimization system, DSO.ai, that Synopsis has deployed at multiple customers now, and they're taking advantage of this system to push their PPA further. Here's an example from design space optimization where a customer had a target leakage. This was the best known result they had. And then after automatically exploring the design space, we were able, DSO.ai was able to find a right point where you had 30% better leakage, meeting the same TNS, and all done automatically. So if I look at it, if some of you have been to the Hot Chips conference earlier in the year, Art presented a very interesting result from DSO.ai that is on the right-hand side here, where the customer had a baseline, there was a target set, and using DSO.ai, they were able to automatically go through the curve and generate the absolute best result they could get. Now, there are two possible results here. One of them is the blue one, and the other one is the purple at the bottom. The blue one is running DSO.ai untrained. Essentially, it's learning on the fly. As it's running the design, it's learning on the fly to see what the best possible operation would be. However, if it was trained, if we fed the training data, you could even do better. So that's the result you see at the bottom. You get much better power at the same time TNS is maintained. So very important result. It also tells you that beyond the tools and algorithms, AI is becoming an important piece of the puzzle for us to do PPA, get PPA and productivity. That's not the end of the story. While it's great, there's also another element to what the users do. So they're running their designs multiple times. They are getting new RTLs every day. They're getting new architectures. They're getting new constraints every day. So they're rerunning the design over and over. They're trying to look at different settings to see what the best possible mode of operation is. They're debugging their design. So a lot of data is generated as they are running these designs. So what are you going to do with this data? So today the designers really wade through this data and try to find this, make sense out of it, to find where they should focus on. What's the next steps to take to get the best PPA, close their design, or if there's a bug, where's the bug coming from? What's the root cause? So this system in Synopsis is an analytics system, which we call the analytics platform with a web-based UI and a cloud-based server that's automatically capturing data as the user is running their designs, capturing all kinds of metrics throughout the whole project, from block to block or from different steps in the block, storing them in a database in a structured way, and then analyzing them, generating deep insights for the customers and the users to use. For instance, if there's a critical path, why is it violating timing? What is the reason? What's the root cause? Which part of the system is creating that delay? Is it the cell delay? Is it the interconnect delay? Is it clock skew? Is it some other kind of mechanism? So this analytics insights data can immediately point them to the right problem and go for the right solution. So really, the triple play here, the Fusion platform, which brings the entire system together, AI platform, which automatically explores multiple different configurations in a very efficient way, and then the analytics platform, which allows the user to focus and generate deep insights into their design and tools. Together, the triple play is key to the SysMoore era. Here's an example of a customer who used all three of these systems: Fusion Compiler, RTL to GDS Complete Flow. They were able to get 11% improvements in power, 11% automatically using the DSO.ai system. Well, 11% is impressive enough, but what's more impressive that it only took one engineer to do it. In the past, they did the same thing. It took 3 experts for multiple months to get to the solutions that DSO.ai came up with. So essentially, again, as we move towards the SysMoore era, the systemic complexity is becoming imperative to employ these new techniques and new solutions that we are offering. Let's talk about variation. It's an important part of the problem we have today. As we go from node to node, it's becoming increasingly apparent that variation is a big part of the headache now. So as cell delays get smaller, voltages get lower, you're near threshold, noise comes into play, variations are huge, they're bigger than the values themselves. So what do you do? So designers are really using a lot of their own methodology, really characterizing their libraries at multiple sigma, running Monte Carlo simulations to see where the problems may be, and then using that information to really design for variability. At Synopsis, we realized that solution for the problem, and we have created a technology which we call Primeshield product that automatically analyzes the robustness of the system, robustness of your circuit, robustness of every endpoint, and tells you, by doing the sensitivity analysis, tells you how sensitive this path is going to be to variations and how likely you're going to meet or violate timing. This is important to build your circuits robustly. So we've created robustness metrics. These are besides the PPA metrics that you may have seen. Robustness metrics are a key part of today's designs, and Primeshield is able to analyze, at the same time optimize for robustness metrics. There's a new concept called voltage slack to identify how far you're resilient to voltage variations. If the voltage drops, when will you violate your timing? So there's a concept of voltage slack that is generated out of Primeshield. And here's a customer that with a CPU core that use Primeshield to do robustness analysis, to do sensitivity analysis, and find out where the robustness was weak in the system and improve robustness by 9%, improve 9% voltage slack in this situation. Again, now hundreds of paths that could have failed timing even after you thought it was good, could have failed timing in silicon, were protected by using Primeshield technology. So important for today's productivity and getting better designs out. Now let's look at energy consumption. So power is a first order metric, right? I think everybody who talks about optimizing PPA today, power is the first thing on their mind. I mean, they know timing is important, but power is the first thing on their mind. So what are we doing? So first of all, let's look at the landscape. What's happening with power? First is the global energy consumption has increased about 7x in the last 50 years. 7x by every country, consuming more and more of power in the form of oil, in the form of coal, or whatever that may be. But there's an observation now. The consumption of global energy is expected to slow down, so it's flattening. The amount of energy that's being that you would expect to consume in the next few years, and that's due to multiple reasons. However, the energy consumption of electronic components, of communications, of devices is expected to accelerate. So it's expected you have many TVs running in your home, your laptops, you have cars, automotives, and everything that are running. The consumption of power is going to increase rapidly in the coming years. So of course, everybody wants to consume less. We need to save power. We need techniques to reduce power. Why is this happening? Again, the demand for chips, whether there's a demand for cloud computing and demand for mobile computing and demand for personal computing and things like that. All of them are increasing at 15 to 20% range every year. So that pushes the power consumption quite a bit up. So what are we going to do? What are we doing at Synopsis to tackle the situation? I heard some people say earlier that power is something we need to look at for the whole spectrum, end to end, and I totally agree. The whole spectrum, from the very beginning, from software all the way to silicon, power has to be considered all the way. Now, why is it important to consider it at the very beginning? Because that's where you have the most opportunities. You could, just analyze power at the end of the flow and then squeeze a milliwatt here, a milliwatt there. You can get 1 to 2% power, but that's not the scale you're looking at. You want to reduce power by 10%, 20% or more. And you can only do that by looking at from the very beginning, looking at the architectures, looking at software consumption, and then looking at the right vectors to use and pushing them through the entire flow. So in the beginning, you have billions of cycles, hundreds of billions of cycles. Then you narrow down to hundreds of millions, and then to a few 100,000. So architecture to RTL to implementation to sign off, the whole spectrum has to be looked at to optimize your power. So what are we doing at Synopsis to enable that? So end-to-end power is a must-have for this SysMoore era. Platform Architect is the tool that allows you to explore your power architectures very early in the stage. So this is where you get the best gain for power. If you choose the right architecture, if you get the right analysis at that time, you can actually gain a lot at the very beginning. Then VCS, high performance simulation, generating vectors and analyzing power at RTL, whether it's Spyglass Power or use Prime Power RTL, RTL Architect, all of them in concert, either analyzing power or optimizing power, and finding the right RTL structure to get the power is important. Now, Zebu Power, the only high speed simulator, power emulator that is available and is really a powerful way of generating vectors that you would use to optimize power. So Zebu Power vectors can be fed into either RTL Architect, Prime Power. They can also be fed into Fusion Compiler, during implementation, and then also into sign-off system. So really the whole system works in concert to get you the best power in this whole situation. And this is augmented by using UPF with power intent early in the flow and design-aware components. These are available at Synopsis as well. So the whole thing is one single solution that works in concert and gets you the best power in the entire flow system. And here's an example from a mobile GPU where it used an overall system, Zebu Power, getting the cycles from there, the cycles of interest that you may have, and feeding them into Fusion Compiler to optimize for power for those cycles, and then validating in Prime Power to make sure that the results are actually accurate. So using this system not only improves the power by 10%, but also you get 10x improvements in simulation because using Zebu Power, much faster system. So overall, software-driven power exploration, RTL-driven power exploration, all the way into gates and sign-off is a must to get end-to-end power. All right, so let's get to the next level, next vector we have to look at. System of chips, 3D IC design. So it's going from system on chips to system of chips. So what is really driving this technique? What is driving this technology to go further? First is integration of chiplets. So a number of designs are being done at different nodes. They're being optimized for their own nodes. Not every chip that you use in a system is at advanced node. Some of them may be 28 nanometers, some may be 16 nanometers, some are actually advanced. So integrating those chips in a way so that the communication between them is efficient is important. So that's one driver towards it. And the second one is disaggregation. As the amount of functionality that's being added to chips, the requirements are getting bigger. So the design size is getting bigger. But you can't really design that big a chip. So there's reticle limitations. There's also yield limitations. So really partitioning and disaggregating the chip is the only way to go forward to reduce your cost and improve your yield. So again, while we are doing this partitioning and integration, you need to keep in mind that you're doing it in a way that you can analyze the entire system. You cannot just break the chips and then validate them one by one. You really have to look at the entire system and be able to confidently say this whole system is going to work. So you need a system that actually enables you to do all of that. So at Synopsis, we have three parts to the solution. One is the interface IP, which is selecting the right IP for communicating between the chips. Second is the design process itself, which is architecting 3D architecture, and then constructing it, then analyzing it, and then optimizing it. And finally, the manufacturing. On the interface IP side, Synopsis offers a number of IPs. And they can be chosen depending on the configuration you have, depending on the requirements you have, the speeds you need. A number of IPs are available to select for 3D IC design. Now, let's go to the design process of 3D IC. So I think, as I mentioned earlier, there are two drivers towards this 3D IC design. One is the applications like Ethernet switches or networking switches or optical switches, where you are actually trying to integrate those chips, and so that the communication between them is small. So this requires, understanding what the IOs are, where the bumps should be, how to align them between different processes, be able to look at the entire system together. So all of that is part of the integration. And the right-hand side is the big chips of servers, big chips of artificial intelligence, AI, where you need to disaggregate the design. I mean, AI systems need communication between the die and the memory, because near memory compute is very important. So all of that together is driving the need for 3D IC design. So what's happening out there in the industry today? So how are people designing these chips? With much difficulty, with a lot of ad hoc methods. There are different people doing different things on the entire chip. There are SoC designers, there are signal integrity analyzers, there are system designers, there are package designers, there's a sign-off team. They're all doing their own things at their own place, in their own tools, with their own data. And then they're communicating or handing off either through text files, or they're handing off through spreadsheets, or sometimes it's phone calls. And you can imagine the amount of errors that can happen here, the iterations that may happen between these teams. And of course, you'll leave PPA on the table. Now, certainly not a good way of going about it. And there's an opportunity for here in the SysMoore era for us to provide a solution that can bring all of this together, and you have one single platform that can enable you to do 3D IC design. So again, all of this, today's techniques are fragmented point tools, poor abstraction. Abstraction is key, because if you wanted to analyze the entire system, you can't load the entire system into memory. You need some ways of abstraction. Inefficient co-design capabilities. Since everyone is doing their own things, they're not seeing each other's effects, so they can't co-optimize at the same time. So a lot of opportunities here. So at Synopsis, we have created a system which is a single platform, a design platform that provides all the way from 3D pathfinding, architecture exploration, implementation, sign-off, optimization, in one single system that is a single data model that enables the entire platform 3D IC design. So how does it look like? So 3D IC compiler is single data model. It enables exploration, architectural exploration early in the flow. That means if you want to see which chips go where and what the effect on thermal is going to be, what the density of bumps is going to be, how do you design bumps for them, what the density of TSVs is going to be, the heat profile, and all of that can be done very quickly with efficient engines at the very early stages. And of course, after you're done with exploration, you have design creation. So you have to construct all of these elements. You have to construct the bumps, you have to align the bumps, you have to create the right amount of TSVs. And all of that has to fall together in such a way that the entire system is actually working. Then after design construction, you have routing, die-to-die routing, HBM routing, RDL routing, DFT, you have timing analysis, you have thermal analysis. The great news is it all can be done in one single system. You do not need to hand off to anyone else. I mean, if you want to get a quick feel of what the thermal is going to be, you can actually do it. So that's the power of single platform for 3D IC design. And if you really want to do it right, if you want to get the best PPA out of it, this is the only way to do it. And here's two examples of two customers where they saved from weeks to hours with die-to-die routing, automatic die-to-die routing, and HBM routing in 3D IC compiler, automatic shielding, and the unified flow allowed another customer to do thermal analysis, PI analysis, timing analysis in the same cockpit. So amazing, I mean, compared to what people have been doing in the past, this is the system that allows you to do a 3D IC design in a much more comprehensive way and correct by construction. Finally, in terms of manufacturing, so Synopsis doesn't manufacture chips, but we do enable manufacturers to be able to debug their designs, 3D IC designs. We also go to in-field optimization. As I mentioned before, you don't stop at tape outs. You can continue to optimize in in-field. So this is a great segue into the next topic, which is closing the loop between design and field, the silicon lifecycle management. So yeah, gone are the days when you can hand off the chip and you can go back home. Now, we cannot be blind to what's happening in the chips. There's so much data in these chips, there's so much information in the chips as they are running. So we can harness that data and get more information on how this chip is functioning, what kind of parameters are being used there, and how can we optimize the chip further, or perhaps there's a failure coming, we can predict the failure of the chip. So the whole silicon lifecycle management ecosystem is built with the Synopsis whole total solution. The first is really inserting monitors into the chip. These monitors are, process monitors, temperature monitors, voltage monitors, security monitors for that matter. These are all inserted at the design stage. And these monitors are then generating data as you do in-field, either test optimization or you do some system upbring or you're running in the field. These monitors are generating data that can be harnessed and that can be fed back into the designers or to the users of these devices. They can tune their parameters to optimize them further. And if there's failure coming, they could actually tune the parameters to prevent those failures. And the products and tools that Synopsis offers in these for this whole situation is one is insertion of these sensors with our MooreTech technology that we acquired in 2020. We had the Primeshield technology to analyze robustness. We have the Yield Explorer to do root cause analysis. We have the Qualtera Silicon Dash system that is the first silicon-based analytics that actually collects data, generates deep insights, and provides guidance to what should be done next, and of course, TestMax. All of that together is another element to boosting your performance and preventing failures. Here's an example of a customer who actually inserted power PVT sensors, then analyzed the design as it was running in the field, and was able to change the voltage and frequency, input voltage and frequency to get better performance out of the chip. So these are the things that we are able to do now. I mean, in the past, it was very difficult to do, but we have the tools, we have the technologies that can enable you to do that. Finally, if I wanted to conclude, we have 6 different vectors that we are embarking on to help with the SysMoore era. Design-specific architectures, energy-efficient designs, continuation of Moore's law, multi-die system, silicon lifecycle management, cloud AI techniques, data analytics, big data processing. All of these together, if you combine them together, and the power of all of them together is really the era that's feeding into the SysMoore complexity and helping you to unflatten the curve and get to the levels of performance, power, and area that we are used to. Finally, the closing thoughts. We are entering into the SysMoore era. So I explained to you what that is and what are the challenges in that era, what the opportunities are, and what kind of innovations that we are doing in this situation. Fusion, AI, and analytics are 3 key elements that are helping us scale the industry, scale through node to node. And finally, Synopsis innovations are there to address PPA, address productivity, address resilience, address longevity of the designs, security, and safety. All of that put together is crucial in the era of SysMoore, And I hope I gave you enough information as to what is happening out there and what we are doing to tackle the situation of slowing on Moore's Law. Thank you very much.